Okay, very good afternoon. Are you getting my voice, ma? Boys, am I audible? Students, am I audible, ma? Are you getting my voice?
கேக்குது மேம்.
Okay, ma, very good afternoon. Am I audible? Are you getting my voice? Boys, are you listening?
எஸ் மேம்.
Yes, ma. Okay, ma. Okay, ma. Is it visible? The slide is visible? Boys?
எஸ் மேம்.
Oh,
தெரியுது.
okay, ma. Okay. So, okay, ma. Very good afternoon. Okay. Okay, very good afternoon to all. Now, we are going to discuss about solid mechanics. Okay. In GATE exam. So let's start. Okay, the slide shows the solid mechanics syllabus. If you talk about solid mechanics, there are few chapters are important. The first one is introduction, and second one is stress. Then third one is shear force diagram and bending moment diagram. Then fourth one is principal stress, stress transformation, and fifth one is bending stress. Then after the bending stress, then sixth one shear, seventh flexural, then theory of failure. So there are 8 basic chapters. Okay, these are the 8 basic chapters. The first one is introduction, then stress, shear force and bending moment diagram, principal stress, then stress transformation, bending and shear stress, flexural, and theory of failure. Okay, these are the 8 basic chapters. So the first 4 is the basic chapters and another 4 application of solid mechanics. Is it clear? So then next topic, torsion, pressure vessel, then column and spring. So in the solid mechanics syllabus, the first chapter is bending moment and shear force in statically determinate beam. Okay, so do you know about the statically determinate beams? Simply supported beam, then overhanging beam. Okay, then what is the type of statically determinate beams? The first one is simply supported, then overhanging beams. Okay, then statically indeterminate means fixed beam and continuous beam. Okay, so first topic, bending moment and shear force in statically determinate beams. These topics it depends upon the cantilever beam, overhanging beam, simply supported beam. So these are the 3 beams are called as statically determinate beams. Cantilever beam, simply supported beam, then overhanging beam. Okay. The next topic, The statically determinate beam is the cantilever beam, simply supported and overhanging. Next, introduction to simple stress and strain relationships. Okay, so it covers the topic what are the types of stress, tensile stress and compressive stress, and strain means longitudinal strain, lateral strain, then volumetric strain, and relationships. The relationships means elastic constants. Okay, so the relationship means elastic constants. So the elastic constants, the modulus of three types of elastic constants are in stress strain relationship. The first one is Young's modulus or modulus of elasticity. Okay, it is denoted by capital E. It is denoted by capital E. So Young's modulus or modulus of elasticity. Then another topic, second relationship, bulk modulus. So bulk modulus, it is also denoted by K. Okay, capital K. Then third modulus, shear modulus. Okay, the shear modulus is also called as modulus of rigidity. Okay, so modulus of rigidity. Then third one is symbol bending theory. So theory of symbol bending, then flexural, then shear stress. Okay, then shear center. So shear center of various cross sections. For example, I beam, T beam, then circular beam, then rectangular beam. Okay, then next topic, torsion, uniform torsion. The torsion means is a twisting movement. Okay, it is a twisting movement. Then next topic, the transformation of stress. So transformation of stress means stress distribution, principal plane. Okay, then buckling of column. So long column and short column, it covers the topic about various theories used to determine the critical load. The first one is Euler's theory. Then second one is Rankin's theory. Okay. So the buckling of column is to determine the crippling load, to determine the failure load or buckling load. Okay, the two types of theories are used to determine the critical load. The first one is Euler's theory, then second one is Rankin's theory. Okay, this is the last topic, combined and direct bending stress. Okay, so direct stress and bending stress. So direct stress, it is developed from load, and bending stress is developed from movement. Okay, is it clear? So in the last topic, combined and direct bending stress. Okay, ma. So this solid mechanics have the 4 to 5 marks in gate exams. Okay, so the weightage is low, but this because if look at solid mechanics, it is the basic subject of DRC, design of reinforced concrete, and steel structures and structural analysis. Okay, it is the very basic subject. So the subject is very important. Okay, ma. So please study very careful. Okay, it is a basic subject of DRC, steel, and structural analysis. Okay, that's all, ma. So it covers the stress, introduction to stress, then shear force and bending moment diagram, then theories of failure means the principal stress, stress transformation, then bending and shear stress. Okay, so flexural theory and theory of failure. Okay, these are the basic chapter. Then is the main application is the torsion, uniform torsion. Okay, spring. Okay, then circular shaft, hollow shaft. It is the application of torsion. Okay, then buckling of column, then combined and direct bending stress. So that's all. Okay, ma. So let's start. The introduction of stress, introduction of strength of materials or solid mechanics. Okay. So first, you should know the what do you mean by strength? Okay, what do you mean by strength? The strength means the resistance to failure is called strength. It is a material property. Okay, so strength means what? The resistance to failure is called strength. It is a material property. For example, M20. So what do you mean for M? Anybody know? M means what? Response me, ma. What do you mean? What do you mean by M? So M means mix. Okay. So M20 means mix 20. Mix 20 grade. So 20 means the compressive strength of concrete. So 20 is FCK. FCK is equal to characteristics compressive strength is equal to 20 Newton per mm square. Okay. Then M15 means, for example, FCK is equal to 15. So Newton per mm square is also called as megapascal. Okay. So the failure, resistance to failure is called as strength. So the strength is also divided into 4 types: tensile, compressive, and shear. Okay. Then bearing strength, then flexural strength. Okay. Then it is the basic definitions. What do you mean by strength? Then what do you mean by stiffness? Okay. Then stiffness. Stiffness means resistance against deformations is called as stiffness. This is the secondary design property. It is also denoted by K and delta. Okay. So resistance against deformations. So the deformation means change in length, change in dimension. Okay. The change in dimensions or elongations, the deformation is also called as deflection. Okay. The deformation is also called as deflection, change in dimension, then lateral strain, longitudinal strain. So the volumetric strain. So it is also called as deformations. Okay. So it is also denoted by K and delta. Then what are the assumptions? Okay. What are the assumptions? The first assumption is material is continuous. Okay. No voids or no cracks. It is also called as material is continuous. Then second point, material is homogeneous and isotropic. First, it should know that what do you mean by homogeneous and isotropic. Okay. For example, homogeneous means, for example, um, you will use the different material, wood, timber, iron, so gold, okay, aluminium, brass, but the material have the three coordinates x, y, and z. Suppose you cut the any direction at any point direction, the material have so same mechanical properties. It is called as homogeneous. Okay, at any point in one directions. Okay, same properties. So what are the mechanical properties? First you should know the what are the mechanical properties. So the mechanical properties means, okay, first one is stress, then second one is strain, stress strain curve, then Young's modulus, shear modulus, and bulk modulus, then Poisson's ratio, then compressive strength, then tensile strength. Okay, these are the mechanical properties. So the mechanical properties are in same at any part, any cutting point or any cutting point of the any direction. It is called as homogeneous and isotropic. Okay, so isotropic means is the fine grain material. For example, the material have same mechanical properties. Okay, but you act in any directions. Homogeneous, what are the difference between homogeneous and isotropic? The homogeneous means the materials at any point in one direction. So the material properties are same or equal at any point in one direction means it is called as homogeneous. So the material have the same property at one point, at any point, okay? At one point and any directions, okay? So directions are any direction. For example, x directions, y direction. So it is called as isotropic. Then orthotrophic. So orthotrophic means, okay, at one point in perpendicular directions, the properties are different. So the material have different mechanical properties. Okay. Please mute your mic. Please mute your mic.
என்னென்ன பைத்தியக்காரி மாதிரி கேட்குறான். 2000 rupees per cup holding அனுப்பிச்சேன் மேம்க்கு.
Mute your mic.
ஆமா 2500 rupees per cup holding அனுப்பிச்சேன். ஊ ரிசீவ்டுன்னு கேட்குறேன்.
Boys.
யார் வாங்கினா cup holding advance.
Boys, mute your mic.
கம்பெனி பேரு
Boys, don't disturb ma.
கம்பெனி அந்த கம்பெனி பேரு
Mute your mic, please.
நான் அந்த ஸ்கிரீன்ஷாட்டே அனுப்பிச்சுட்டா கூகுள் பே ஸ்கிரீன்ஷாட்டு.
Number 30. Number 30. Register number 30.
அதே என்ன சொன்னீங்க அதே
Register number 30. Register number 30. What are you doing, ma? Register number 30. What are you doing? Number 30, register number.
சென்டிங் வேலை எல்லாம் தெரியுமா?
Register number 30. Number 30. Friends inform பண்ணுமா அவனுக்கு கால் பண்ணி. Register number 30. Register number 30.
வேலை இருக்காங்க.
Number 30.
கன்ஃபார்ம் ஆன வேலை இருக்கு. கன்ஃபார்ம் வேலை இருக்கு. பர்மிட் வாங்கியாச்சு.
Yeah, 1 minute ma. 1 minute.
இவ்வளவு எப்படி பேசுறேன் நான் பர்மிட்டை கொடுக்கூடாது. ஹலோ சொல்றா.
Okay. Hello.
ஐயோ இந்த மைக்கு ஒரு பெரிய தொல்லை. சார் டிராக்டர் அனுப்பிச்சுடுறீங்களா நாளைக்குங்களா? இன்னைக்கு ஒரு தள்ளி பார்த்துட்டாங்கன்னா அப்புறம் நாளைக்கு கொடுப்பேன்.
So, okay, ma. Sorry for the disturbance. The students are instructed to switch off your mic. Okay, switch off your video and audio. Okay, please don't disturb to others. Okay, ma. Now we will continue. So orthotrophic means the material have different mechanical properties at one point in perpendicular directions. Okay. Then it is the non-isotropic and anisotropic means the one point in different directions and properties are different means it is called as non-isotropic. So for example, the material have with cracks and voids. Okay. Then homogeneous plus isotropic means the material is homogeneous and isotropic means at any point in any directions the same properties. Okay. Then last assumptions, the self-weight neglected. The stress-wise strain starts from origin to these assumptions. It is the basic definitions and basic concept. Okay. Then superposition principle is valid. The superposition principle means the algebra sum of various effect is equal to the total effect. Okay, the effect means it is also called as the summation of shear force, a summation of vertical load, summation of horizontal load. Okay. Then the limitation of superposition principles. Okay. These topics are the basic concept of solid mechanics just for reminder. Okay. The first one is the linear elastic members. It obeys the Cook's law. So the Cook's law is valid and loads must be up to prescribed loading. The loads must be up to the prescribed loading means it is a linear elastic material. First, you know the difference between linear and non-linear. So the linear means, okay, the linear means the stress-wise strain. Okay, it is the stress-wise strain graph is the inclined line. Then also the what do you mean by linear? The load does not change with time. The load is constant. Okay, so the linear means the load does not change with time. It is called as linear. The load change with time. The vary with time means it is called as non-linear. For example, if linear load, it is known as a point load, UDL. Okay, the non-linear load means, for example, earthquake load, seismic load, then wind load. Okay, these are the non-linear load. Then what are the limitations? The first one is linear elastic material and second one is the deformations are very small. Okay. Then deep beam. So the deep beam means the torsion developed due to loading which causes distortion in shape. What do you mean by distortion? Okay. It is the strain, change in dimensions, change in deformations. This is also called as distortion in shape. Okay. Then shrinking of support. Okay. The axis gets curved or distorted. Distorted means deflected. It is the shear strain. Okay. It is the deflected. Then another applications is the long column. So in the long column, it may fail, buckling or bending failure. Okay. So in the long column may fail, buckling or bending failure. Then torsion. Okay. The torsion means is the twisting movement. Okay. The figure shows the distorted shape shaft. Then Saint Venus theory. Okay. First you know the what do you mean by stress, then strain, Okay, the Saint Venus theory's principle is valid only for the sudden change in any parameter. Any parameter means, for example, length, okay, then breadth, then depth, then diameter, okay, the change in dimension, change in diameter by original diameter, it is also called as circumferential strain, okay, circumferential strain. Then volumetric strain means is the change in volume by original volume, okay. These are the sudden change in any parameters. Okay, ma. So let's start in the introduction to stress. Okay. First, you know that what do you mean by stress? The internal resistance developed against deformations per unit area is called stress. Okay. So you simply studied stress is equal to load by area. Okay. It is the formula. Okay, not definitions. The stress means the internal resistance developed against deformations per unit area. So internal resistance is also called as stress. Okay, is a resisting force divided by unit area. So in the box, okay, unit of stress is equal to Newton per meter square or Newton per mm square. The kilopascal means kilonewton per meter square and megapascal means Newton per mm square and gigapascal is equal to 10 power 3 Newton per mm square. Okay. So sigma is equal to, sigma means stress is equal to load by area, P divided by A. It is a simple formula. Then types of stress. So the classification of stress, it is also called as stress distribution or transformation of stress. Okay, it is divided into two types. The first one is normal stress, then second one is shear. So the normal and shear, it is divided into two types. The first one is direct and another one is indirect. So direct means you have already studied tensile stress and compressive stress. Okay, the tension member is also called as beam, okay, or concrete beam or steel beam. So tension member means, for example, beam or also called as tie. Then compression member means strut or column. Okay, strut or column. So the normal stress, normal direct stress, it is divided into two types. The first one is tensile, then another one is compressive. Okay. Then indirect stress. The indirect stress means due to the stress is developed due to bending movement or bending stress or flexural stress. Okay, listen here. The tension member means, for example, you should like a beam or tie. Okay, flexural member means it should have the direct and indirect stress, bending stress and flexural stress. Then what are the flexural members in building components? Beam and slab. Okay, the beam and slab is also called as flexural members. Okay, so how to determine the bending stress? F is equal to, here F is equal to M divided by Z. So M is the moment, Z is the section modulus. Okay, so sigma stress is equal to load by area, P divided by A. Okay, then tangential force per unit area. So shear is divided into direct and indirect stress. The direct stress means simply it is also called as shear stress. Okay, tau shear, it is denoted by tau is equal to F divided by A. Okay, F divided by shear force divided by area. Okay, then indirect stress is equal to torsional stress. Okay, torsional stress, it is developed from twisting movement. Okay, so the tau shear stress is equal to T divided by plastic section modulus. ZP is also called as plastic section modulus. Okay, so the tau is equal to T divided by plastic section modulus. Okay, so shear stress, the direct stress means direct shear, shear force divided by area. Then indirect means it is developed from twisting movement. Okay, it is also called as torsion, uniform torsion. Then what are the strain? Very easy, ma. Longitudinal strain, lateral strain, then circumferential strain, then volumetric strain. Okay, the first one is the normal strain. It is also called as longitudinal strain. Longitudinal means the changes in length. So strain means change in dimension by original dimensions. Okay. Then shear strain, then volumetric strain. Okay. Then circumferential strain. First you know that volumetric strain, circumferential strains, longitudinal strain and lateral strain. The first one is longitudinal strain. Change in length by original length. Okay. So circumferential strain means change in diameter divided by original diameter. Okay. Then volumetric strain means change in volume divided by original volume. That's all. So these are the types of strains. Okay. Then material properties. Okay. What are the material properties? First one is elasticity. So elasticity means you already know that ability to retain or to regain shape on removal of external force. Okay. So to regain its original shape after the removal of external load, it is called as elasticity. Okay. So the material should regain original shape after the removal of external load. Then plasticity means the member undergoes the permanent or plastic deformations at constant load. Okay, it is the plasticity. Then ductility. So the material can be made into thin wires. For example, steel is a ductile material. Okay, so listen here. The steel is a ductile material means, okay, the steel is used to make the steel rod, steel wire, and steel plate and steel sheet. Okay, so the steel can be made into any shape. It is called as ductility. Okay, then malleability is the properties crushed into thin sheet. Okay, it is called as the malleability. Then brittle. For example, brick is a brittle material. Fails suddenly. Okay, it's like the crushing failure. For example, brick. And the last one is grip. So the plastic or permanent deformations due to constant load with time. It is called as grip. Okay. Then what are the stress strain curves? For example, the steel is low carbon steel. Low carbon steel means is a mild steel. What is the grade of mild steel? Fe 250. Okay. And what are the grades available in steel? Mild steel, Fe 250 and HYST, high yield strength deformed steel bars, Fe 4 and 5 and Fe 500. Okay. Okay, first you these are the stress strain curves. After finishing our class, I will share these notes. Okay. Okay. These are the relation between Young's modulus, shear modulus, and bulk modulus, and Poisson's ratio. Okay, it's very important formula. Okay, so the 1 mark and 2 mark questions are taken from this elastic constants. Okay, the first is capital E. The capital E means Young's modulus or modulus of elasticity. So the capital E is equal to 2G into 1 plus mu. So the capital E, it is denoted by Young's modulus or modulus of elasticity. Then G, capital G means shear modulus or modulus of rigidity. Okay. Then mu is the Poisson's ratio. Okay. K is the bulk modulus. It's very important formula. Please note it down. Capital E is equal to 2G into 1 plus mu. Then capital E is equal to 3K into 1 minus 2 mu. And mu is equal to 3K minus 2G divided by 6K plus 2G. Then what are the relation between 3 modulus? Okay, is the last formula. What are the relation between 3 modulus? Is the last formula. The capital E is equal to 9 kg divided by 3K plus G. Okay. Okay. So the next topic, temperature stresses. Okay. The stress is developed from change in temperature. Okay. The stress is developed from change in temperature. It is also called as thermal stress or temperature stress. Okay. It is the indirect stress. Then external loads are direct stresses. Okay. Then alpha, the coefficient of linear thermal expansion, it is the coefficient. Okay. Then it is a strain developed per unit change in temperature. The alpha is a material property and is constant for given material. So, what is the value of coefficient of linear expansion of steel and concrete is equal to the alpha steel is equal to alpha concrete is equal to 12 into 10 power minus 6 per degree Celsius. Okay. Please note this point. Alpha steel. Okay. Alpha steel is equal to alpha concrete is equal to 12 into 10 power minus 6 per degree Celsius. Okay, ma? So, one question is taken from thermal stress. Composite steel bars. Okay. You have already studied in mechanics of solid subject, composite bar, common bar. Okay. So, the composite bar means it's made of different materials. For example, RCC, reinforced cement concrete. So, the RCC means reinforced cement concrete. So, the reinforced cement concrete means that what are the materials are included in the RCC? Concrete plus steel. Okay, the concrete plus steel is that there are the two different materials are acting in combined unit. It is called as composite steel bars. Okay, is made of different materials. For example, RCC. So, what are the formula for calculating stress in composite bars? Okay, compressive stress sigma C is equal to P divided by AC. Sigma S means stress in steel. Okay, the sigma is equal to stress. Sigma S means stress in steel is equal to load P divided by area of steel, and sigma C stress in concrete is equal to P divided by AC. AC means area of concrete. Okay, these are the basic formulas. Okay, next 1 hour we are going to discuss some important gate questions from solid mechanics. Okay. Then parallel. Okay, the uniform no warping as there is no bond and no support. Both copper and steel will expand individually. It is called as the common bar. Okay. Next is very important. Coop stress or circumferential stress. Okay. Then Coop strain formula. Okay, ma. This is the second topic, complex stress and strains. Okay. Biaxial, then principal stresses, principal plane. Okay. Then shear stresses, maximum shear stress. These are the topics that are included in the complex stress and strain. So, 2D or biaxial or plane stress system. The first system is 2D, okay, two-dimensional, or biaxial or plane stress system means all the stresses will be developing in one perpendicular plane only. Okay, in one perpendicular plane only. Okay, these are the basic formula. Shear and maximum principal stress and minimum principal stress. Okay. So what do you mean by principal stress? The normal stresses across the principal plane is principal stress. Okay. The normal stress across the principal plane is principal stress. Then what do you mean by principal plane? The plane on which only principal stress will be acting. Okay, listen here. So on principal plane, shear stress is 0. Okay, so keep in mind, on principal plane, shear stress is 0. And location of principal plane. What is the formula? Location of principal planes. Tan 2 alpha is equal to, so the alpha is the angle. Okay, tan 2 alpha is equal to sigma x minus sigma y divided by 2 sine 2 alpha minus tau xy cos 2 alpha. So tan 2 alpha is equal to 2 into tau xy divided by sigma x minus sigma y. Okay, ma, is the first formula. The location of principal plane. Okay. And maximum shear stress. Please note the point. The tau max. Tau is also denoted by shear stress. The maximum shear means tau max is equal to plus or minus sigma 1 minus sigma 2 divided by 2 is equal to root of sigma x minus sigma y by 2 the whole square plus tau xy square. Okay. So in 2D system, there will be two maximum shear stresses of equal magnitude but opposite in nature. And third topic, Morse circle. Okay, the Morse circle means is a graphical method. Okay, to determine the principal stresses. So first of all, we will discuss about the what are the formula for principal stress, principal plane, location of principal plane, and maximum shear stress. It is the analytical method for calculating the principal places. Okay. Then Moore circle is the graphical method given by Otto Moore. It's a basically developed for 2D stress system. Okay, is the graphical method. And is it one question from Moore circle? The radius of Moore circle. Okay, the capital R, radius of Moore circle is equal to sigma 1 minus sigma 2 divided by 2. Okay. Is it clear? Okay, ma. Next topic is shear force and bending moment diagrams. Okay. This topic is very, very basic concept. Okay. It is very important. Okay. In our civil engineering field. So what do you mean by shear force? Then bending moment. Shear force means is the vertical unbalanced force. Okay. The shear force means it is the vertical unbalanced shear force. Okay. Then bending moment means the force into distance. Okay. Okay, what are the types of support? Okay, the roller support. Okay, please see this figure. The figure shows the roller support here. For example, old bridges. And second support is the hinged support or simply supported. It is also called a pinned support. Okay. So hinged support means it has two reaction components. Okay. The roller support house, it has one reaction components. And another one support is fixed support. It have horizontal reaction, vertical reactions, and rotations. Okay. So listen here. It's very important basic concept. So the roller support means it have one reaction. It has one reaction component, one vertical reaction. Okay, ma? Please note the point. Note it. Roller support means it has one reaction component. Okay. Refer this figure. Then hinged support means it have two reaction components. One is the vertical reaction, then another one is the horizontal reactions. Then third one is the fixed support. It have three reaction components. The first one is vertical, horizontal, and another one is rotation. Okay, the fixed support have movement. And internal hinge. So the internal hinge means you should like this figure. And what are the types of loads? Concentrated or point load. Okay. The first one is the point load or concentrated load. Refer this figure. The W mean is the point load. Okay. The unit of point load is Newton or kilonewton. Then second load, uniformly distributed load. Okay. Uniformly distributed load. For example, dead load, wind load. Okay. Refer this figure. The unit is kilonewton per meter. Okay, per meter. So UDL load is per meter. Okay, kilonewton per meter or newton per mm. So what is the unit of uniformly distributed load? Kilonewton per meter or newton per mm. Third one is very important, uniformly varying load. Okay, it should act the entire area. Okay, uniformly varying load. Uniformly distributed load means it should act along the length. So it is called as uniformly distributed load. But here, uniformly varying load means the load is should act along over the entire area. UVL. Okay, it's a triangular load or trapezoidal load. Okay, the example is triangular or trapezoidal load. So the unit is kilonewton per meter or newton per mm. And couple. So the couple, clockwise and anti-clockwise movements. And bracket. And what are the types of beams? Okay, so what are the types of beam? The first one is simply supported beam. Refer this figure. Okay, the first end is simply supported. Then right side end is the roller support. Okay, it is called a simply supported beam. Here, propped cantilever. The propped cantilever means one end is fixed and another end is simply supported or roller or hinged. It should also called as the propped cantilever. Okay, next is very important topic. Shear force diagram and bending moment diagram. Okay. So the diagram showing variation of shear force along a structure, it is also called a shear force diagram. Okay, ma. So what do you mean by shear force? Is the vertical unbalanced shear force. Okay. It is the sign conventions. Okay. Upward means positive, downward means negative. Next one is the bending moment diagram. So the algebra sum of moments either to the left or to the right of the sections. Okay, the summation of moments, bending moments. Okay, sagging moment, it is the positive sign. Okay, the gouging moment is the negative sign. And is very important formula. Relation between rate of loading means is the W, shear force and bending moment. Okay. What is the relations? F is equal to dm divided by dx. So d means differentiate, rate of change of. Okay. Next is very important definitions. Point of contraflexure. Okay, is very important. The point of contraflexure. So the point where bending moment changes sign or curvature of the beam reverse its directions. So the changes in sign, okay, the bending moment changes in sign. This point is also called as point of contraflexure. Okay, so the point of contraflexure means the point where bending moment changes sign or curvature of the beam reverse its directions. Okay, so the bending moment is always drawn on the tension side. So the point of contraflexure determines the portion at which reinforcement is provided. Then another one is absolute bending moment. So the absolute bending moment means the maximum magnitude of bending moment over a beam. Okay, so the maximum magnitude of bending moment over a beam. So the maximum bending moment is also called as absolute bending moment. Is it right? Next one is slope and deflection. Okay, the slope means change in rotation of point is also called as slope. And deflection means change in position of point. It is called as deflections. Okay, first you should know the what do you mean by slope and deflection. The slope, the change in rotation of point is called as slope. Change in position of point is also called as deflection. Okay. So the deflection, it is also called as displacement. So the displacement of a point from initial position to final position, an elastic curve is called deflections. Then slope means the angle between tangent drawn to the initial point and final point, an elastic curve in radius is called as slope. Simply change in rotation of point. What are the methods are used to determine the deflections? Okay, you have already studied in strength of materials paper. Okay, what are the methods are available to determine the deflection of the beam? Okay, the Macaulay's method, okay, conjugate beam method, Maxwell method. Okay, so the lot of methods are available here. Okay, double integration method. Okay, just go through the what are the methods are available in calculating deflections. Okay, this is very important. Relations, the y means deflections. Okay, is very important. Please note it. Y means deflection and dy by dx means slope. Okay. Then another differentiate d square y divided by dx square is also called as curvature. 1 divided by capital R is equal to m divided by ei. Okay. D power cube y divided by dx cube is equal to force or dm by dx. F is also called as force. And d power y divided by dx cube is equal to df divided by dx is equal to w. Okay. W means the rate of loading. So F means force. Okay. The next topic, center of gravity and moment of inertia. Okay, ma. So what do you mean by centroid? Okay. You have already studied in engineering mechanics, mechanics of solids. Okay. What do you mean by centroid? Define centroid. The point through which entire area is concentrated. Okay. It is called a centroid. Okay. Centroid means the point through which entire area is concentrated. This is applicable for plane surface area. Then center of gravity. So the point through which entire mass on weight is concentrated. So the point through which whole mass, entire mass weight. This point is also called as center of gravity. Okay. Area means centroid. Then mass or weight is also called as center of gravity. So what is the formula for calculating centroid? X bar is equal to AIXI divided by AI. And y bar is equal to AIYI divided by AI. So AI means area. Okay. X in the horizontal dimensions, Y vertical dimensions. X means breadth, Y means depth. Then moment of inertia. Okay. Moment of area. So in the moment of area, it is divided into two types. First one is the area moment of inertia. Then another one is mass moment of inertia. So the area moment of inertia means is the resistance of a member against externally applied moment is moment of inertia. Okay. For example, is the bending moment and twisting moment. Okay. Then second, moment of inertia. First one is moment of area. Okay. The unit is mm power 4 or meter power 4. So the moment of inertia indicate the distribution of given area so about a reference axis. Okay, so what is the unit of moment of inertia? I is equal to meter power 4 or mm power 4. Then is very important theorem, parallel axis theorem. It's the transfer formula, parallel axis theorem. So Ix is equal to Ixc plus Ay square. The least moment of inertia of a given area will be with respect to the centroidal axis. It is also called as parallel axis theorem. Okay, so least moment of inertia of a given area will be with respect to centroidal axis. Okay. A perpendicular axis theorem means the moment of inertia about a perpendicular axis to the plane of area is polar moment of inertia. The polar moment of inertia, it is also denoted by capital J. Okay, the capital J. So moment of inertia, it is denoted by capital I. Polar moment of inertia means it is denoted by J. Okay, first you should know the formula for moment of inertia for various cross sections. Okay, ma. So the first one is circular section. What is the formula for moment of inertia? The capital I is equal to pi by 32 d power 4. And second sections, rectangular, BD cube divided by 12. Then hollow circular, I is equal to pi divided by 32 divided by into d power 4 minus small d power 4. Capital D means outer diameter and small d means inner diameter. Okay, then the last one is product of inertia. So the product of inertia is equal to Ixy is equal to dA into integration of dA into xy. Okay. The next topic is theory of symbol bending. Okay. Already studied about theory of symbol bending for mechanics of solids paper. What is the formula here? It's very important formula. Please note it down. E divided by R is equal to M divided by I is equal to F divided by Y. Okay. So this equation is also called as bending equations or flexural equations. Capital E divided by R is equal to M divided by I is equal to F divided by Y. Okay. The capital R means radius of curvature. I means moment of inertia. M means moment. Okay. F means bending stress. Okay, ma. E is the Young's modulus and small y. It's the linear distance from neutral axis. Okay. Y is the linear distance from neutral axis. Okay. Two questions are available from this topic. Okay, please, it's very important. But what do you mean by section modulus? The section modulus, it is denoted by Z is equal to I divided by Y max. Okay. So I divided by Y max. So I is the moment of inertia. The Y max is the distance. Then flexural rigidity. The E and I. E means Young's modulus. I means moment of inertia. Okay. It is called as flexural rigidity. First, you should know the section modulus formulas for different sections. For example, square, rectangular, hollow rectangular, and circular, and hollow circular. Okay. Then triangular section. Okay. Okay. So the next topic, shear stress in beam. So a direct shear means shear force divided by area. So indirect shear stress means it should be developed from torsions. Okay. So the flexural shear stress or indirect shear stress due to bending action in a beam. The first one is pure shear. Okay, for example, deep beam. This is the basic formula. It is very important formula, ma. Please note it down. Tau x shear stress. Tau x is equal to VA y bar divided by I into B. Okay, V is the shear force at cross section due to vertical or transverse loading. Then A is the area. The y bar is the centroidal distance. Then B is the breadth. I is the moment of inertia. It is the basic formula for calculating the shear stress. Okay, please note it down. So the tau x is equal to VA y bar divided by I into B. Okay, then second formula, the average shear stress. So the average shear stress is equal to V divided by cross section area. Okay, is the shear force divided by cross sectional area. And relation between maximum shear stress and average shear stress is very important formula. The relation between tau m. Tau m means maximum shear stress. Tau average means average shear stress. Okay. So tau A is equal to B divided by BD. The relation for rectangular but square system is equal to 3 by 2 is equal to 1.5. So the relation between maximum shear stress and average shear stress in square or rectangular section means is equal to 1.5. Okay. Tau maximum divided by tau average is equal to 1.5. The second one is solid circular. So the relation between maximum shear divided by average shear is equal to 4 divided by 3. Okay. Maximum shear stress divided by average shear stress is equal to 4 divided by 3. Then triangular. Okay. Tau max divided by tau A is equal to 3 by 2. Here. Same as square and rectangular section. Okay. Then first you should know the how to calculate the moment of inertia for various sections, I section, I beam, T beam, symmetrical I beam and unsymmetrical I beam. Okay. The basic formula is tau is equal to VA y bar divided by I into B. Okay, ma? So now we are going to discuss about some important gate questions from solid mechanics. Okay. If you have any doubt, please ask me. Okay. The question number 1 from stress strain topic. Okay, one question from stress strain topic. A metallic rod of 400 mm length and 50 mm diameter, okay, when subjected to a tensile force of 80 kilonewton at the end, experiences an increase in its length by 0.5 mm and the reduction in its diameter by 0.01 mm. So the Poisson's ratio of the material is here Unknown is the Poisson ratio of the material. Okay. What are the given data? Length. Okay. Length is equal to 400 mm. Then diameter 50 mm. Okay. So read the questions very careful. Then tensile force. The tensile force is equal to 80 kilonewton. Experiences an increase in its length by 0.5 mm. So increase in length means is the change in length. Okay. So 0.5 mm. So del L. Del L is equal to change in length. And reduction in diameter. So reduction means is the degree. So the decrease in diameter is equal to 0.010 mm. Okay. So the Poisson's ratio, what is the formula for Poisson's ratio? The Poisson's ratio is equal to, it is denoted by mu. Okay. What is the formula? Lateral strain divided by linear strain. So lateral strain means epsilon lateral. Strain is also called as epsilon, denoted by epsilon. So divided by epsilon linear. So what is the formula for lateral strain? Del D divided by D. Change in diameter divided by original D. So here change in diameter is equal to 0.010. Okay. Then original diameter is equal to 50. So divided by change in length. Change in length is equal to 0.5. Okay. Here experience an increase in its length 0.5. Okay. So L is equal to original length is equal to 400. Again, substitute the values and we will get 0.16. Okay. So the Poisson's ratio of the rod material is 0.16. Is it clear, ma? So the Poisson's ratio, the formula is equal to lateral strain divided by longitudinal strain. So the lateral strain means del D divided by D and linear strain by del L divided by L. Change in diameter by original diameter divided by change in length by original length. Okay. So the answer is 0.16. Any doubt? Any doubt for calculating Poisson's ratio? Please ask. Any doubt, ma? Students? Are you listening? Boys? Which number? 803. Response, ma. Any doubt? Okay. The next question. A solid cube of side 1 meter. Okay. A solid cube of side 1 meter is kept at a room temperature of 40 degrees Celsius. Okay. So cube means it have the equal dimensions in all four sides. Sorry, all sides. Okay. The coefficient of linear thermal expansion is the alpha. The coefficient of linear thermal expansion of the cube material. So alpha is equal to 1.2 into 10 power minus 5 per degree Celsius. And bulk modulus is 180 gigapascal. Okay. K. So bulk modulus K. If the cube is constrained all around and heated uniformly to 60 degrees Celsius. Okay. So the first temperature T is equal to 40 degrees Celsius and second one is 60 degrees Celsius. Okay. So then the magnitude of volumetric stress. Volumetric stress. So stress is also called as sigma. Okay. So volumetric stress means sigma V. Okay. Induced in due to heating is. So the unknown is volumetric stress. Okay. So how to calculate the volumetric stress? So the formula. the volumetric stress is equal to, for example, what are the given data? The temperature. Okay, you should find the first change in temperature. So T1 is equal to 40 degrees Celsius and T2 is the 60 degrees Celsius. So the change in temperature 60 minus 40 is equal to 20 degree Celsius. Okay. So the cube side 1 meter. Then K, bulk modulus is equal to 180 gigapascal. Okay, ma? So the alpha value is equal to 1.2 into 10 power minus 5 per degree Celsius. Okay, so now coming to the solutions, K, bulk modulus is equal to sigma V divided by epsilon V. So the sigma V is equal to bulk modulus into epsilon V means volumetric strain. Sigma V means volumetric stress. Okay, K is the bulk modulus and volumetric strain. So what is the K value? 180 into 10 power 3 into volumetric strain means, okay, it is the cube. So lateral strain epsilon L plus breadth epsilon B and epsilon height. Okay. So here please note this point. The strain in length, breadth and height. Okay. So the section is cube. Okay. It have the same strain. Okay. So 3 into is, you should also write 3 into epsilon L. Okay, ma? Here the cube is problem, solid cube is here section. So the epsilon L linear strain is equal to breadth, change in breadth and change in height. So you should also write here 3 into epsilon L. Epsilon L means length, change in length. Okay, you substitute the K values 180 into 10 power 3 into 3 into epsilon L. So epsilon L means change in length. How to calculate the change in length? Due to induced in thermal stresses, L into alpha T. Okay, please note this point. L into alpha T divided by L. Okay, for example, epsilon L is equal to del L divided by L. So here L and L cancel. So K 180 into 10 power 3 into 3, then D into D, alpha into T. So alpha value 1.2 into 10 power minus 5 and temperature changes 20 degrees Celsius. Okay. So you substitute the values in the above formula. Sigma V is equal to K into epsilon V. We will get sigma V is equal to 129.6 megapascal. So the answer is 129.6 megapascal. Okay, ma? Then question number 3. If the principal stresses in a plane stress problems are sigma 1 is equal to 200 megapascal and sigma 2 is equal to 120 megapascal. Okay, it is a two-dimensional plane. So it has two types of principal stresses, sigma 1 and sigma 2. So sigma 1 is equal to 200 megapascal and sigma 2 is equal to 120 megapascal. So the magnitude of the maximum shear stress will be, so now we will calculate the magnitude of maximum shear. Shear means tau max. Okay, ma? So what is the formula for tau max? The tau max is equal to sigma 1 minus sigma 2 divided by 2. So 200 minus 120 divided by 2 is equal to 40. Okay, so the answer is 40 megapascal. Okay, ma? The next question. A cantilever beam is loaded as shown in the figure. The maximum shear force in the beam is equal to, okay, the maximum shear force. So which place the maximum shear force is developed? Okay, for example, the maximum shear force is developed in support only. Okay, It's developed to support only. So the support have a high shear force. Okay. Then now apply the equilibrium equations. Summation of vertical force is equal to 0. Now taking moment about B, so R minus, R is the reactions, okay, is the upward reaction, so plus R minus, it is the parabolic loading, okay. So parabolic loading means how to calculate the shear force? Load into area, so, okay, the load is the W. What is the area of parabolic? 1 by 3 into AB, so 1 by 3 into L. So R minus 1 by 3 WL is equal to 0. So R is equal to 1 by 3 into WL. It is reactions. So the answer is option D. Okay. So the maximum shear force is developed in the support. Okay. Is it clear? So capital R is equal to 1 by 3 into W into L. Next question. For cantilever beam shown in the given figure, the deflection at C due to double M. So C point is here. Okay, ma? Due to double M, capital M. Applied at B point. So the first support is A. So here the middle point is B and C. The last point is C. So the deflection at C due to double M applied at B is equal to, okay. So the unknown is del C. Del C means deflection at C. So how to calculate the deflection at C? Del C is equal to deflection at B because the C point is here. Okay. Here, this point. Listen here. At point B. Okay. This point deflection is called as delta B. Okay. So del C is equal to delta B plus here length is equal to 2L divided by 3. So theta means rotations because deflection drawing here beam. Okay. Okay, deflection drawing means it should like okay. This point is B. This is theta. Okay. Theta. So del C is equal to del B, deflection in at B plus theta B. Theta B means rotation into 2L divided by 3. Okay, so what is the formula for deflection at B? Deflection at B means it is the here fixed support, the simply supported. So M L square divided by 2EI. The first span AB, L is equal to L by 3. Okay. So M into L by 3 the whole square divided by 2EI. Plus theta B. Theta B means rotation, slope. The slope in at point B. So M L by 3 divided by EI is the slope formula into 2L divided by 3. The length of BC. Okay. Then substitute the values. We will get 5 ml square divided by 18 EI. So the option B is correct. Okay. So the deflection at C is equal to deflection at B plus theta B into 2L divided by 3. The next question. The beam is loaded as shown in the given figure. Okay. The Kinch reaction at P here, ma. the Kinch reaction at B is equal to. So first this portion A to C. The beam is divided into two shapes. The first shape, this one, A is the fixed support. So B is the reaction is the downward reaction. Then separate portion BC. B is the upward reactions. And C is also the fixed support. Okay, it's the span BC carry the point load B. Okay, BC have the equal length. So how to calculate the Kinch reaction at B? Okay, so delta B is equal to delta AB is equal to delta BC. Okay, delta AB is equal to delta BC. So the AB means deflection AB because the first beam. Okay, what is the formula? Here reaction is here, RB reactions. Okay, reaction at B is here. So RB into L, length, the span AB length is L cube divided by 3EI is equal to delta BC. BC have the load, point load P. So what is the formula for deflection BC? WL cube. So PL cube divided by 3EI plus PL square divided by 2EI and L minus this portion. Okay, this deflection from reaction B for span BC. So RB into 2L cube divided by 3EI. Okay. So finally, we will get reaction at B is equal to 5P divided by 18. Okay, the simple formula, the beam is divided into two separate portions, the span AB and span BC. Okay, you should apply the formula del B is equal to del AB is equal to del BC. Okay, because it is the three moment equation theory. The deflection at B is equal to deflection at AB is equal to deflection at BC. Okay. The next question. The beam is loaded as shown in the same question, but only one is different. Okay. The previous question, we calculate the Kinch reaction at B. Here, the deflection at B. The same question, only unknown is different. Deflection at B, okay, is unknown. So in the same, the beam is divided into two separate portions, but already we calculated RB is equal to 5 divided by 18P. Okay, then the formula delta B divided by AB is equal to RBL cube divided by 3EI. Okay, deflection at B is equal to span AB. Okay, delta AB here. So 5 divided by 18P is the reaction at B into L cube divided by 3EI. We will get 5P L cube divided by 54EI. So the option B is correct. Okay. So the same question, the previous question, we calculate the Kinch reaction at B. Here, we calculate the deflection at B. Okay, ma? Is it clear? The next question. For the overhanging beam shown in figure, the Kinch reaction at B. Okay, the beam is the overhanging beam. The Kinch reaction at B. Okay, so see this figure. A is the fixed support, B is the simply supported, and at N C has the point load 100 Newton. Okay, ma. So it is easily separate the first at point B. You will consider the downward load 100 Newton. At the same point, you will consider the upward load 100 kilonewton. Okay, listen here. For applying compatibility conditions, okay, we will consider at point B, you assume downward load 100 Newton and upward load 100 Newton. So plus minus is equal to 0. So the structure, the beam is safe. So no issues. Okay. Then now at point B have downward load 100 kilonewton. At point C, 100 kilonewton is also here. Then upward load 100 kilonewton is also here. So these two forces are acting combined couple, clockwise. Okay, clockwise couple. Okay, so what is the formula? So clockwise moment 100 Newton meter. Then at point B 100 kilonewtons. There are one load 100 kilonewton at point B. Then one moment is acting there. So for this beam, one downward load 100 Newton at point B is acting. Then 100 Newton meter moment is acting at clockwise moment. Okay. The formula, so at point B 100 Newton means here support A, the reaction is half into 100 is equal to moment 50 kilonewton meter. Okay, so the moment is equal to 50 kilonewton meter. So RB is equal to 100 Newton. So the M divided by L is equal to 150 divided by 275 plus also 100 Newton is also available here. So 100 plus 75 is equal to 175 kilonewtons. So the hinge at beam B is 175 kilonewtons. Okay. So in this question, you should apply the compatibility equations. Okay. You assume the one upward and downward are is equal magnitude. Then you will proceed the formulas and get the answer. The next question. The question number 9. The state of stress at a point for a body in plane stress is shown in the figure below. If minimum principal stress is 25 megapascal, then the normal stress sigma is in megapascal. So the unknown is normal stress sigma x. So sigma x is the unknown. Okay. So it is the two-dimensional stresses. What is the formula for sigma x? So sigma 2 is equal to, okay, sigma 1 is here. Then, so minimum principal stress is assume as sigma 2. So sigma 2 is equal to sigma x plus sigma y by 2 minus the root of sigma x minus sigma y by 2 the whole square plus tau xy square. Okay, here the minimum principal stress is sigma 2. So sigma 2 is the 25. Okay, ma? Okay. So sigma x is the unknown, is the normal stress. Sigma y, refer the drawing. Sigma y is 70 divided by 2 minus root of sigma x minus 70 by 2 the whole square plus tau here. Shear stress 50 megapascal. So you substitute the sigma 2, sigma y and tau value. Then we will get the sigma x value. Sigma x is equal to 80.5 megapascal. Okay. 1 minute. Any doubt, please ask me now. 1 minute wait, I will note the attendance. Okay, ma. So next question. Shear force and bending moment diagrams for a beam ABCD as shown in figure. It can be concluded that. Okay. Okay, first you refer the first drawing. At support A. Okay, the support A. It is the rectangular shape shear force. Okay. So now you will remember it is the point load. Okay, then point B, C, D. It also have the rectangular shape. So here the point load is acting. Okay. So first drawing is the shear force drawing. Then second one is the bending moment drawing. Here bending moment have the triangular shape. Okay. So it is the point load, bending moment. So in the option A, the beam has 3 support. So the beam has 3 support means the support A, okay, this is one support, and support D, this is the second support. And third one is, it is a load acting point. It is not the support, okay. So the first option is wrong. Then second, NA is fixed. Here, suppose shear force drawing is the simply supporter. Fixed means, okay, suppose is the start from rectangular to rectangular. This is the point load shear force. The NA is fixed means here, this point. Changes in shear force drawing, so NA is fixed is wrong. Then third options, couple of 2000 Newton meter acts at C here. Okay, Newton meter means it is the bending moment drawing. Please see this point. Here 1000 Newton per meter, the upper point here 3000 Newton per meter. So what is the difference? 3000 minus 1000 is equal to 2000 Newton meter. So here some changes in triangular shape bending moment, changes in triangular shape. So here this point is acting movement. Okay, the clockwise movement is acting. So the couple is acting. So the couple of 2000 Newton meter acts at Z is the correct answer. Okay. Then last options, a uniformly distributed load confined to portion BC only. So BC is the rectangular shape. Okay. Only point load shear force diagram is the rectangular shape. Suppose UDL means the shape of shear force is triangular. Okay. So this option is wrong. So the answer is C. Couple of 2000 Newton meter acts at C. Okay, ma? Is it right? The next question. The state of stress at a point okay for a body in plane stress is shown in the figure below. Okay, all of you refer the drawing here. 20 megapascal stress. Okay, so tensile stress and compressive stress 50 megapascals. Okay, then find the shear stress acting on plane AB. All of you listen here. This is the plane AB. Okay, this is the 140 degree. Okay, the total inclined plane angle is equal to 180. So over here 180 minus 140, so it's the 40. Okay, then here 180. Then these portions in the horizontal portions here. Okay, the 180. Okay, this portion is the 90. So 90 means the 40, here 40 means is the 50. 90 minus 50. Okay. So total 180 here. So 180 minus 50. So theta is 130. Okay, this point. Okay. So 180 minus 50 is here 130 degree. Okay. So what is the formula? Tau theta is equal to sigma x minus sigma y divided by 2 sin 2 theta minus tau xy cos 2 theta. Okay. So sigma x, substitute the sigma x value 100. Okay. So sigma y is the 50. So is the downward. So minus. Okay. The compressive forces. And theta is equal to sin 2 theta 130 degree minus tau xy 20 and cos 2 theta. So 2 into 130. So the answer is minus 77.3329. Okay, ma? So the answer, the find the shear stress acting on plane minus 77.3329. Okay, next question is the column. A square cross-sectional steel column of length 3000 mm is pinned at both ends. Okay, pin means simply supported. Okay, the column needs to be support on axial compressive load of 1000 kilonewton. So here is the square. Okay, is the square column. Square column length is equal to 3000 mm is simply supported at both ends. Okay, ma. So the column needs to support an axial compressive load. It's 1000 Newton using a factor of safety 2. Okay. In the computations of Euler's buckling load, the minimum cross-sectional area in mm square of the column. Take Young's modulus for steel is equal to 200 gigapascal. So E steel is equal to 200 gigapascal. So the question is minimum cross-sectional area of the column. Okay, here it is the square columns. Okay, ma, it is the square columns. Then the length is equal to 3000. So if the both ends are pinned. Pinned means effective length is equal to K into L. LE is equal to K into L. So 1 into L is equal to 3000 mm. Okay. The effective length is equal to K into L. K means load end coefficient. So here simply supported means both ends pinned means here. So 1. 1 into L. So 3000 mm. Then what is the using the Euler's theory here? Euler's buckling load. So what is the formula for Euler's buckling load? PC load pi square EI divided by LC square. So E, Young's modulus for steel, 200 into 10 power cube I. I means here 200 gigapascal. Okay. You should convert the gigapascal to megapascal. So 10 power 3 into I because it is the square. So what is the formula moment of inertia for square section? A power 4 divided by 2. Okay. Divided by L's effective length. Effective length is equal to K into L 3000 mm. So 3000 square. So substitute the values is equal to load PC. So load is equal to 1000 kilonewton into load factors. Okay. Into load factor is equal to into 2. So 2000 into 10 power cube. Okay. So substitute the values. You should get the one side of square A. One side of the square. Okay. A is equal to. Then you will calculate the area square. A square is equal to 10467.73 mm square. Okay. Is the next question. Is the last question, ma. The cross section of two solid bars made of same materials. Okay. Is the last question. Please listen here. The cross section of two solid bars are made of same material are shown in figure. The triangular cross sections has flexural rigidity. Flexural rigidity means E into I. While rectangular cross sections has flexural rigidity R2. Both the sections have the same cross-sectional area and same bases shown in figure. There is a ratio of R1 by R2. Okay. The flexural rigidity for triangular section ratio divided by the flexural rigidity of rectangular section area. Okay. The first one is triangular and second one is rectangular. Here. Okay. Refer the drawings. The ratio of R1 divided by R2. So flexural rigidity means E into I. So R1 is equal to E into I1 divided by E into I2. We'll get the E cancel. Young's modulus is same. Cancel. So I1 divided by I2. So I1 means moment of inertia for triangular section BH cube divided by 36. And I2 for rectangular section BH cube divided by 12. For example, BD cube by 12. Okay. Then you will get the final h cube divided by 3 into h by 2 the whole cube. Okay, so finally you will get the 8 divided by 3. Okay, so R1, the ratio of R1 divided by R by 2 is the 8 divided by 3. Okay, ma? So that's all. So next class, we will discuss about torsion. Okay, then spring. Okay, then pressure vessels. The remaining topics. Okay, so the next class we will discuss about uniform torsion, buckling of column, and combined and direct bending stress. Okay. So, sorry, any doubt, please ask me. Any doubt for today class? Do you have any queries? Okay, ma. Shall I wind up? Okay, thank you. Okay, thank you, ma. You may leave.